let me start by saying that this is the last of the colloquia for this semester. So we'll pick things up again in the fall after this. So today it's a real pleasure to have Ronald de Wolf from the University of Amsterdam, and he's also a senior researcher at CWI. Ronald is, I think, many people here are doctors of philosophy. Ronald is the one person who actually has a master's in philosophy, as in actually philosophy. So Ronald has worked extensively on various aspects of quantum computation, including lower bounds and computational complexity. He actually also worked on this notion of dequantization, where you prove something via a quantum argument and then dequantize it to get the classical result. Obviously, and also he's worked extensively on quantum algorithms, including algorithms for optimization, which he'll tell us about today. So Ronald, welcome, and looking forward to hearing your talk.
Thanks so much. Let me share my slides. Let's see, do you see my slides now? Yeah. All the slides are nothing but the slides?
One of the slides.
So you should now be seeing the full title slide.
Yeah. Okay,
good. So let me get started. So this is going to be a survey talk about quantum algorithms for optimization problems. I will not keep track of the chat, so I hope the moderators will interrupt me if there's an important question that I need to answer at that point in time. So what is optimization? Well, the general problem, let's look at minimization. We have some function f, so it could be a very general object, and we want to find its minimal value when x comes from a certain set k. So k is going to be our feasible set of allowed solutions, the things we can plug into our function. And then we're supposed to find, or at least approximate, the minimal value. And this, of course, is a basic problem in analysis and math. It's also a very useful problem. In fact, lots of the uses of computers in industry and elsewhere are of optimization form. Right. So here's a simple example: finding the shortest map, finding the shortest route on a given map. This is a simple example. It can be solved very efficiently. Designing a more energy efficient chip, that's also an optimization problem. The function there that you want to minimize would be the energy usage of the chip. Training your neural network to detect cats. This is, of course, a massive application of optimization of all sorts and forms in the last 10 years. And this is just to illustrate the sort of the versatility and the usefulness of being able to solve optimization problems. And I want to distinguish two kinds of optimization, namely the discrete and the continuous setting for optimization. And in discrete optimization, the variables that you can play with, so that the variables that determine your set k of feasible solutions are discrete. So think about this as either bits or integers. Right, and you can think here so discrete optimization problems include the shortest path algorithms that I already mentioned, things like matching algorithms, max flow, min cut in a network, and also many NPHard problems. In fact, very often, if you formulate an optimization problem and you make it discrete, so you force your variables to be, let's say, binary or integer, your problem becomes NPHard. And this includes all sorts of constraint satisfaction problems, like satisfiability of the Boolean formulas, traveling salesman problem, integer linear programs. And this should be contrasted with the case of continuous optimization, where the variables that you can play with are continuous. So typically here, your variable is a vector of n real numbers. Could be constrained or could be unconstrained. And here's a bunch of sort of algorithms that you could use. In the case of continuous optimization, there is gradient descent, which is a very versatile workhorse of continuous optimization. There are also much more structured problems like linear programs, semidefinite programs. And of course, there's also non-convex optimization, which is sort of the most general optimization problem you can think of. Or you could think of a mix of these. So I actually borrowed here the logo from an earlier program of the Simons Institute, namely a program that wanted to bridge between continuous and discrete optimization. And let me just mention two of these bridges. In fact, they will sort of make an appearance later on in this talk. So one is you can take a discrete problem. A famous example is finding the maximal cut in a graph, right? That's a typical discrete problem because you want to select a subset of the vertices of the graph in such a way that the number of edges that are being cut by the bipartition is maximized. This is a very discrete problem, but actually the best way to solve it is to relax it to a continuous optimization problem and solve this using an SDP solver. This gives you the best approximation that we know how to find in polynomial time. Another interesting bridge example is the example of Laplacian linear system solving. So solving linear systems, so something of the form Lx equals B, where L is a given matrix and B is a given vector. This occurs all over the place, and typically you need superlinear time to solve these things. So more than n squared time if L is an n by n matrix. But if L has a special form, namely if it's so-called symmetrically and diagonally dominant, which means that it sort of corresponds to a Laplacian of a graph, you can actually use discrete techniques, so-called graph sparsification techniques, to sort of slim your linear system down to be much sparser and then efficiently solve the sparser linear system. And this will also resurface at some point later in my talk. Right, so this is just setting the stage of discrete and continuous optimization. And how can quantum computers help? That's of course the sort of the main purpose of this talk. So I want to claim here that faster optimization is one of the main potential application areas of quantum computers, right? And then of course you would ask, what are the other ones? Well, I think that the two other main application areas would be cryptography. And in that case, I'm thinking both about breaking crypto schemes and making secure other crypto schemes. And of course, the most famous of all is simulation of quantum systems. And I think these three are probably the main application areas of quantum computers for the future. And the good thing about optimization is that several new quantum algorithms have been discovered in the last 5 years. And the purpose of this talk is to survey these things, to survey what we know, not just the things from the last 5 years, but I will spend more sort of attention to those recent developments. And I'm going to focus here on what I'm most familiar with, because those are the things I can sort of semi-competently talk about, and those are provable speedups. And in particular, that means I'm not going to talk about many things that have gotten a lot of attention, which is heuristical methods. So I'm not going to talk about the adiabatic algorithm. I'm not going to talk about simulated annealing or regular annealing. And I'm also not going to talk about variational quantum algorithms, such as the quantum approximate optimization algorithm due to Fari, Goldstone, Goodman. But since Eddie Fari will be on the panel, I suspect that later in the panel discussion, we will also talk a little bit about sort of more heuristic algorithms, such as these variational algorithms. And just to set the stage for what might happen in the panel discussion, let me just sort of very briefly say what these variational algorithms do. The idea is that you have a low depth quantum circuit, which is parameterized by a few parameters, for instance, a few angles in the gates in the circuit. And the idea is that you sort of want to set these parameters in a way that would optimize a certain function. So what do? You run your circuit, you measure the output, or maybe you sort of repeatedly to approximate the expectation value of the output. And then you have a classical loop that adjusts the parameters to improve the behavior of your circuit. And then you hope to do something useful. And I'm using the word hope here because not that much provable is known about the behavior of these variational algorithms, but one of their sort of useful features is that they're small enough to be able to run on current or very near-term hardware. Right, but for the purposes of this talk, I'm actually going to bracket these variational algorithms, and I will talk about other kinds of speedups. And I want to mention here two big caveats for the algorithms that I will talk about. And I think Matthias Streuer earlier in this series very clearly made the same points, and I just want to repeat those points basically to tell you what are the weaknesses of the kind of algorithms that I'm going to talk about. So the first weakness of these algorithms is that almost all of the optimization speedups that quantum computers give you, at least the ones that I will talk about, are polynomial, typically quadratic or maybe even less than quadratic. And you could ask yourself, is this any good, right? And you could say, well, you know, any speedup is worth having. That's great. Of course, this is good. But there's an issue here of the sort of the prefactors that are hidden in the speedup, right? So suppose you have a quantum algorithm. Let's say it's Grover based. It runs on some search space of size n. So the runtime is order root n. That's how a theorist would write it. But the order, the big O, would hide a large constant because one quantum operation could be pretty expensive. Right, and then you want to compare this with the classical cost for solving the same problem. That would be linear in n rather than square root, but it would have a much smaller prefactor, right? So large C would be sort of the cost of one quantum operation, and little c would be the cost of one classical operation. And classical hardware is so good that this little c is just much, much less than the big C. And you can just calculate like what is the instance size that you need before the sort of the quantum algorithm becomes faster than the classical algorithm. And the instance size is the square of the ratio of these two prefactors, capital C over little c raised to the power 2. Right, and this is for quadratic speedup. If your speedup is polynomial but less than quadratic, it's even worse than this. And then you want to ask, okay, so what is this ratio of capital C over little c? How much slower is a quantum operation than would be a classical operation? And it's pretty bad. I think Matthias Streuer in his talk, he sort of claimed that there's like 10 to 12 orders of magnitude in between. So let's be gentle here and just assume 10 orders of magnitude. So if capital C is 10 to the power 10 bigger than little c, you only start getting a speed up when your instance size is bigger than 10 to the power 20. And that's pretty bad. I think 10 to the power 20 is not completely ridiculous, but it is pretty large. So this is one big caveat, right? And I think this also means that these optimization speedups, they're not for the NIST computer, they're not for the near term. You need a computer that's big enough to handle such large instance sizes that actually the quadratic speedup, despite its large prefactor, can overtake the classical linear time. And of course, this 10 to the power 10 here, this is just a very sort of rough estimate. It's based on the idea that you need sort of a certain number of physical qubits to encode one logical qubit, and that every quantum operation on those physical qubits is sort of guided by a classical computer that spends a number of operations on implementing or guiding every quantum operation. And it gives you these large orders of magnitude. This is not set in stone. I mean, I suspect that this should come down over time. But for now, it's certainly true that a classical operation is much, much cheaper than one quantum operation. And then the second caveat that I want to mention is the issue about how to access data. So most of the problems I'm going to talk about, they start from classical input, classical data. And this could be, for instance, an input graph, say given as an adjacency matrix, or maybe given as an adjacency list. It could be a matrix in some SDP description. And our quantum algorithm should be able to access this data in superposition. Right now, how do you access data? In a classical computer, you would just store it in a random access memory. Right, and a random access memory that stores n bits of information. You can think of this as a piece of hardware of size roughly n that you can access in time roughly log n. Right, and sort of a qualitative way to think about this is you can arrange your n bits as the leaves of a binary tree of depth log n. And then if you want to read one of those bits, you sort of go to the roots of this tree. You have log n address bits that chart a path through the tree towards the leaf that you want to go to. You look up what bit is stored there and you take it back to the root. This is really a cartoon picture of how random access memory works in a classical computer, but I think it's good enough for the purposes of this talk. And a quantum random access memory should be somewhat similar, right? Sometimes people call this a quantum classical random access memory because I only care here about memories that store classical bits, but that I can somehow access in superposition. So I want to be able to run this unitary here, the unitary that takes I, 0 to I, xi. So something that allows me to access the ith bit of the input. And then it should be coherent, meaning that I could actually run this on a superposition of i's. And this is what I call a quantum RAM. And quantum RAM has gotten a lot of bad press recently. I think a lot of people have been pretty dismissive about this. I think conceptually, there's nothing really wrong with quantum RAM. I mean, I think most people would accept that classical RAM is a reasonable concept. I mean, we use it every day. Of course, in this crowd, quantum superposition is also a very reasonable concept. Otherwise, we wouldn't be here. And if you just put those two things together, you get quantum RAM. So I think quantum RAM is at least a theoretical concept that makes sense and that might be implementable in the longer term. And this is very easy for me to say because I'm not the one who's going to do the implementing. And particularly in the situation where your hardware is somewhat noisy, this is not easy. In any case, the algorithms I'm going to describe in the rest of this talk, they will, many of them will assume some sort of QRAM access to their classical input.
Ronald, can I ask a question?
Yeah, go ahead.
So is there, sorry?
Go ahead.
So is there any proposal how to implement this beyond querying some Oracle function? I mean, an Oracle function obviously gives some kind of quantum RAM, but is there any proposal how to build something like that, where you could have maybe in exponentially long time store information, but then read it out very quickly?
Well, so I think what you mean by Oracle is just this unitary map, right? Without actually saying how it is implemented.
Kind of any Oracle query is a quantum RAM, but of course that's nothing where you can actually store stuff. So is there any proposal where you could actually build something like that, where you could?
So the way I'm thinking about quantum RAM on a high level is pretty similar to the way I'm thinking about a classical RAM, and that is that it's sort of a fixed object of size n. And you shouldn't analyze this in terms of gate complexity, because then you're dead. You should analyze this in how much time a physical object would need to travel from the root to one of the leaves, right? So think of a little train with log n bits starting at the root, and the little train has log n bits inscribed inside of it, and those log n bits they chart a path that this little train can follow to the particular leaf that's being addressed by the log n address bits, right? So the little train goes down that path, looks up the bit that is stored here, puts it in the phase, or puts it in, C-nots it into another qubit, and then goes back to the root.
Is it RAM or ROM? So can I also write data into this thing, or can I only read data from this thing? Maybe that's a way to ask the question.
In some of my algorithms, I'm going to assume that you can classically write. So in other words, that when you're not in superposition, you can actually decide, okay, I'm going to flip the third bit in this RAM. So it's.
But is there a proposal how to do that in a reasonably scaling way? I mean, a theoretical proposal, that's my question.
Well, that depends on what you mean by scaling. I mean, classical RAM is not scaling. If you think about it in the circuit model, if you write it as a circuit, the number of gates is going to be order n, not order log n. And yet people agree that this is not an issue. So in any case, so this little story of a piece of hardware of size log n that travels down a path to pick up a bit and then returns, you should somehow be able to do this in superposition. So you could have some sort of, say, some little block of log n qubits whose position could be in a superposition. And this could travel down these different paths in superposition. And I think this makes some sense, but it's going to be terribly hard to implement it with noise. But I want to move on because I don't think this should be a discussion.
Okay, no, sure.
Shall I move on? Okay, so do these two big caveats mean that quantum computers are useless? I would argue no, but I would argue that they're probably not for the near term. I guess I already said this before. If somebody says that they're going to have some nice commercial applications of quantum computers based 2 years from now, it's an optimization algorithm with a quadratic speedup, I would not put money in that company. But I think for the longer term, these caveats can be overcome. Okay, so now let me move in to discrete optimization and discuss some of the speedups that we actually know for problems in discrete optimization. So the first one is sort of the most general. It's also the sort of the most boring, and that is if you have a function on a discrete domain of size n, let's say it maps the numbers 1 up to n to the reals, you can find a minimum of this function in about square root of n time. This is a very simple application of Grover's quantum search algorithm, which is due to Dürr and Hoyer. Right, so this is not very exciting, but it is very widely applicable. Another example is finding shortest paths in graphs. So this is one of the applications I mentioned in my first slide. This is a problem that's being solved all the time. You know, Google Maps solves this. The navigation software in your car solves this. And And the classical complexity of this problem, so think about the map as an n-vertex graph given as a matrix, let's say, where the ij entry will give you the distance between city I and city j. And then you can find the shortest path in this graph classically in order n squared time. This is Dijkstra's algorithm, which he actually did when he was at CWI. And you can compare that with quantum complexity that turns out to be n to the 1.5. So that's a polynomial speedup, but it's not even quadratic. But it is the best you can get. This is what we know about finding shortest paths. There are also polynomial speedups for problems like matching and many other graph problems. And these typically, unsurprisingly, they use Grover's quantum search algorithm as a black box within a larger, often redesigned classical algorithm. You typically don't take a classical algorithm and hit it with Grover. You typically take a classical algorithm, sort of rebalance the different parts, and then apply Grover to whatever search problem is in there. And I want to zoom in on one recent application of quantum algorithms to graph problems that gives such a polynomial speedup, where again, the main tool is Grover's algorithm, but it's really hidden sort of at the bottom of a large layer of all sorts of classical tricks that you would not need for classical algorithms. And this is the case of graph sparsification. So graph sparsification is an extremely useful tool for if you want to do algorithmic tasks on graphs. Right, and the picture to keep in mind for graph sparsification is you're given this graph on the left here. It could be pretty dense, has lots of edges, and you want to sort of move it to this graph on the right, which has far fewer edges, and yet retains many of the properties that the original graph had. And sparse graphs are good because they're cheap to store. Right, a graph is typically stored as a list of edges. If you have fewer edges, you need less space to store your graph. And it's also typically faster to run an algorithm on a sparse graph than it is to run an algorithm on a dense graph. Let me be a bit more precise. So what is our input? Our input is a graph, let's say with n vertices and m edges. And it's going to be a weighted graph. So all the edges have some non-negative weight. And I'm going to assume that this graph is given as an adjacency list. And what this means is I'm allowed to ask queries of the form, give me the third neighbor of the fifth edge, or give me the seventh neighbor of the third edge. So this is a type of queries I can ask. Right, and this is not unreasonable. If you store your graph as sort of the neighbors of vertex 1 as a list, the neighbors of vertex 2 as a list, etc., you can make such queries very efficiently to your graph. Right, and why am I not using the adjacency matrix format for a graph, where you would just have sort of an n by n matrix? It's because if a graph has m edges and m is much smaller than n squared, then this adjacency list format is a much more efficient way to represent the graph. And what is the goal of sparsification? Well, I already mentioned it. You want to take your graph G, which may have many edges, and you want to reduce the number of edges significantly while preserving many of its properties. And you want to do that efficiently. And what does it mean to preserve many of its properties? So the kind of things that we will preserve of the graph will be spectral properties. And the spectral properties of the graph are very nicely codified in an n by n matrix that's called the graph Laplacian. And the graph Laplacian of the graph G, this is an n by n matrix, and it's going to be the weighted sum of the Laplacians of the individual edges in your graph. So it's going to be a sum of m different matrices weighted. And the Laplacian of one particular edge, let's say the edge ij, that's going to be this ring 1 matrix here. And I don't want to really give an intuition for why Laplacian is a good representation for a graph, but it is a very natural one. And if you prefer to think about the adjacency matrix, then let's say in the case of an unweighted graph, the Laplacian is just a diagonal matrix that has the degrees on its diagonal minus the adjacency matrix. And this is a very good linear algebraic way to represent your graph. And what is it that we want to preserve in sparsification? It's essentially the properties of the Laplacian. So here's a technical definition. So I'm starting with this graph G. And I want to find another graph H, whose set of edges is a subset of the original set of edges, hopefully a much smaller subset. I'm allowed to reweigh the graph, so I'm allowed to change the weight function W. And the number of vertices remains the same. So I start and end with n vertices. I just want to have fewer edges in between those vertices, just like in this picture at the top of my slide. And the property I want to preserve is that for every vector x of n variables, the quadratic form of the Laplacian of g and h should be essentially the same with respect to that vector x. So this is a pretty strong requirement. For every n-dimensional vector x, I want x Laplacian of g times x to be essentially the same within a multiplicative factor of 1 plus or minus epsilon to the Laplacian of h. And LG and LH are not going to be the same matrix. How could they be? Because H is going to be much, much sparser than G. And yet somehow we can preserve all these quadratic forms here. And this is a pretty powerful thing. And just to illustrate one example, suppose you were to start with a complete graph, let's say the n-clique. Then a typical example of a sparsification would be an expander graph. An expander graph is a graph that has a constant degree, so its number of edges is order n, and it shares this property here. So all of the quadratic forms in the Laplacian are preserved, right? So you can really think of an expander graph here as sort of the poor man's version of a complete graph. Now, why do we care about preserving these quadratic forms? Oh, sorry. Let me first say that sparsification is actually, it's possible and it's efficient. So it's for every given graph G, you can always sort of cut down the number of edges to be linear in n, the number of vertices. For concreteness, just think of epsilon here as a small constant, something like 1 over 100 or 1 over 1,000. Right, so then you go from m edges to order n edges. And that's as small as it gets, because if you had fewer than n edges, your graph becomes disconnected. And the good thing is we can also find such a sparsification in near linear time. So it exists, and you can find it very efficiently. This O tilde, by the way, this ignores some block factors. You can think of this as essentially linear time in the input length, right? Because the input length is proportional to m. As an adjacency list, you're just storing a list of edges. So this is essentially linear in the input length. And this is all classical. And it has lots of applications, including, for instance, very efficiently getting approximate min cut or max cut in a graph. Because if you look at this property that's being preserved here, and you plug in the special case where x is a 0, 1 vector, right? So you can think of a 0, 1 vector x as sort of specifying a subset of the vertices. And then it turns out that this left-hand side here, this is just the value of the cut between the subsets specified by your 0, 1 vector and its complement. Right? So what this is saying is, for every possible cut in G, the corresponding value of that cut in H is almost the same, multiplicatively related by, let's say, 1.001. It's almost the same. Right, so if you want to approximate the min cut in your graph, and you don't like dense graphs, what do? You first sparsify it, and then you run a min cut algorithm on the sparsified graph. And similarly with max cut. Max cut is a very different problem because it's NP-hard, while min cut is in polynomial time. But the best possible approximation you can get in for max cut is done in this way. You take your graph, you sparsify it, and then you solve the SDP for the sparsified graph, the Gomans-Williamson SDP. And another thing, and I think this was really the main driving force in the development of sparsification, is to very efficiently solve these Laplacian linear systems that I mentioned before as a bridge between continuous and discrete optimization. So you can solve, if I give you a linear system Lx equals B, let's say L, your matrix, has M non-zero entries, you could solve that linear system in linear time in M. That's pretty good. And it uses sparsification as a subroutine. And this development actually netted Spielman and Teng the 2015 Gödel Prize. This was viewed as a very important development, and these two people were kind of pivotal in the development. Right, and this is all classical, what I said here. I basically just described what graph sparsification is, why we want to do it, and that you can efficiently solve it classically in linear time in the length of the input. Now, of course, I want to talk about quantum. So what's my next slide? Obviously, it's going to be a faster quantum algorithm to do sparsification. And let me just emphasize here that the output here is classical. This is not something like the HHL algorithm where I return the answer as a quantum state. The answer is just a classical description of the sparsified graph. And this was work done by Simon Apers and myself last year. Actually, most of the work was done by Simon. So we give a quantum algorithm that finds an epsilon spectral sparsifier H in sublinear time, essentially square root mn. Again, think of epsilon as a small constant here. Right, and this is a polynomial speedup. For instance, if you start with a pretty dense graph where m is like n squared, then we reduce the complexity from a classical n squared to a quantum n to the 1.5. Again, polynomial speedup, but even less than quadratic. But it turns out that this is the best you can get. We also proved that this is optimal in m and n and epsilon. And we get very similar speedups for these applications that I mentioned before, approximate min cut, approximate max cut, solving Laplacian systems. We can all do this in sublinear time. And let me very briefly sketch how our quantum algorithm works. So its starting point is a classical iterative sparsifier due to Kutis and Chu from 2016. And the idea is, so this iterative sparsifier, this works in a logarithmic number of iterations. And every iteration sparsifies your graph a little bit more. So it's not like you go from m edges to order n edges in one step. You sort of cut the number of edges in half in every iteration. And after a logarithmic number of iterations, you're down to the minimal number of edges. And each iteration of this Kutis-Chu sparsifier, what it does is it first identifies a small set of important edges in your graph, the ones you definitely want to keep in your sparsifier. This is going to be roughly order n edges. Think of that as a very small fraction of the edges. And they identify these important edges by finding a few spanners in the graph. So a spanner is sort of a subgraph that preserves distances, and it's very sparse. So you can find a few spanners in your graph. You can do that classically in linear time, order m. And then, of course, you still have almost all of your edges left because you only took out a very small fraction of them. So what do? You just sample of the remaining edges. You sample half of them and you throw the rest away. And it means that one iteration of this Kutis-Chu sparsifier, it kind of sparsifies by half. It goes from m edges to roughly m over 2 edges. Next iteration goes to roughly m over 4 edges. And this means that after a logarithmic number of iterations, you've actually found a good H. So an H that has order n edges left. And this is all pretty efficient. This works essentially classically in linear time, O tilde m. And our quantum speedup uses two different tools. One is we give a better quantum algorithm to find these spanners in the graph. Classically, this takes O tilde m time, which is as good as it gets. Quantumly, we can reduce this to square root mn. And last but not least, we find the final set of edges. So at the end of these different iterations, we find those using Grover's algorithm. And you might wonder, how does this come up? The reason is we have to keep a very intricate implicit representation of our intermediate graphs. Right? Classically, if you think about this, you start with a graph which has m edges, and you sort of reduce to another graph that has m over 2 edges, another graph that has m over 4 edges, etc. And classically, you have enough time and space to keep those in memory. Right? Your classical algorithm is supposed to work in O tilde m time. It has enough time to just sort of write down all these intermediate graphs. We don't have that time in the quantum case because we want a sublinear algorithm. So we need to go through a lot of tricks using all sorts of implicit representations, using k-wise random strings to sort of downsample our graph in every iteration. And what we end up with after logarithmically many iterations is a very implicit representation of the subgraph H. And then we use a final Grover search over this implicit representation to actually pick out explicitly what are the edges that we're going to retain for our sparsifier. Right, and this picture sort of illustrates this for the case where you start with a complete graph. So this is the G on the left here. You find a few spanners. Those are the red edges. You downsample the others, and you get to this graph here. In this smaller graph with fewer edges, you again find a small number of spanners. Those edges you keep in your sparsifier. You downsample the rest, so you go down to m over 4 edges, etc. Right, and at the end of the day, there's this implicit representation left that has only roughly n over epsilon squared edges left, and we use Grover search to find those. And there's, like I said, there's several layers of classical stuff here that are needed to make this work, including all this k-wise independence, which you don't need in the classical case. So on the one hand, sort of the main quantum subroutine is Grover, which we apply in multiple places. But on top of that, we need to do a lot of classical work that classically would not be necessary. This just to illustrate that you don't just sort of hit things with Grover. You have to do a lot more work to get these speedups. Okay, so I guess this is what I wanted to say about discrete. Oh, no, there's one more slide I wanted to say about discrete optimization. That's, of course, what all the journalists and startups are after, quantum speedups for NP-hard optimization problems. Right? Polynomial speedups for NP-hard optimization problems are very feasible. We have lots of those. Right? Sort of the canonical one is you can speed up the satisfiability problem. Suppose I give you a Boolean formula that has n Boolean variables, x1 up to xn. You can think of this just as a search space of size 2 to the n. Every truth assignment is a string of n bits. If you want to see if there exists a satisfying assignment to your formula phi, one thing you could do is you could just brute force search over all the truth assignments. And of course, you can speed this up using Grover, right? I don't think I'm saying anything very surprising here. And this is the best that we know for things like satisfiability. And for many other NP-hard optimization problems, even this doesn't work. Like you can't just sort of treat this as a brute force search problem and hit it with Grover. Like a slightly more interesting problem is 3-set. Right, you could hit this with Grover. You get an algorithm that takes times square root of 2 to the n. That's actually slower than the best classical algorithm that we know. So classically, there's this very nice random walk algorithm due to Schoening, which solves the 3-set problem in 4/3 to the n. That's better than what Grover gives you. 4/3 is less than the square root of 2. Fortunately, in this case, we can use Grover in a slightly more subtle way. You can still sort of look at Schoening's algorithm and do a search over. So you can think of Schoening's algorithm as a polynomial time algorithm that has a success probability 3/4 to the n, right? So if you repeat it 4/3 to the n many times, you find a satisfying assignment. And this is something we know how to speed up quadratically using something called amplitude amplification, right? So you can hit Schoening's algorithm with amplitude amplification and you still get your quadratic speedup compared to the best classical algorithm. And I want to mention briefly 2 more general techniques that you could use for attacking NP-hard problems. One is Ashley Montanero's quadratic speedup for backtracking. So backtracking is a very general tool that you can use to sort of slightly more cleverly search through an exponential search space, and you can speed this up quadratically. And another fairly general tool is polynomial speedups for dynamic programming. This is due to the Ambainis group. Again, these are polynomial speedups. They're even less than quadratic. And one interesting application here is the best algorithm we know for the traveling salesman problem. This is called the Held-Karp algorithm. It takes time roughly 2 to the n. And you can speed this up polynomially to roughly 1.7 to the n. And this is not super impressive, of course, but there are already subtle things you want to do here, because if you just hit the traveling salesman problem with Grover, you get nothing. Right? Traveling salesman is the problem of finding a route in an n-vertex graph, and the route should go through every vertex exactly once. And there's n-1 factorial such different routes. So of course you could hit this with Grover, solve the problem in square root of n factorial many steps. That's much, much worse than this classical Held-Karp algorithm. And for a long time, we didn't even know any speedup for TSP, despite what the journalists sometimes tell you. And so at least it was sort of gratifying that we can get some polynomial speedup for TSP by speeding up this Held-Karp dynamic programming algorithm. I think this is currently still the best that we know. We don't even have a quadratic speedup for solving traveling salesman problem. I'll mention that as one of my open problems. And these polynomial speedups, that's probably as good as it gets. We don't expect super polynomial or even exponential speedups. And the reason is, if you view satisfiability just as an unstructured search problem, then this Grover speedup is optimal. This was shown by Bennett, Brassard, Bernstein, and Vazirani a long time ago. And then, of course, you could tell me, well, this is not an unstructured search problem. Like if I give you a Boolean formula, there's structure to the set of satisfying assignments, right? So use that structure. And I would be happy to do so, but I have no clue how to do it. And neither do we know how to do it. In the classical case, we don't know how to use the structure in NPHard problems. And this is also the reason why we believe that P is different from NP, and even stronger statements like the exponential time hypothesis. Right? And the same applies to in the quantum case. Like brute force is not going to solve NPHard problems efficiently. We don't know how to use the structure to get anything much better. I guess this ends what I wanted to say about the case of discrete optimization. So let me move on to continuous optimization. I see lots of stuff in the chat, by the way, so moderators, feel free to interrupt me if there's anything that needs attention.
No, we were just having a separate discussion.
Oh, okay.
Yeah, thanks.
I hope you guys are having fun. Good, so continuous optimization. Let me first talk about gradient descent, because that's really kind of the sort of the Swiss Army knife or the workhorse of optimization. So what's gradient descent? I'm sure most people have seen it before. It's some iterative method to find at least a local minimum of some function f. So think of f as a function that takes a vector of n real numbers to one real number. So what do you do if you want to find a local minimum? You start at some point here, you compute the gradients, so sort of the vector of derivatives, and you go down negatively along the gradient, because locally this is the direction of steepest descent. So if you sort of greedily want to minimize your function, you want to move down the gradient by some amount, right? And you get to a new point, you compute the gradient, you move down further, etc. It's a very simple idea, and it will typically take you to a local minimum. Well, not always, but it will often take you to a local minimum. If you're lucky, like you are in this picture, and the function you want to minimize is convex, then a local minimum is actually a global minimum. But even in many cases where your function is not convex, it's still useful to be able to find a local minimum. In many cases, a local minimum is actually pretty good. For instance, this is true for when you're training neural networks. So this is basically what I described before. This is just gradient descent. You start at time 0, take some initial point x0, you compute the gradient. That's the vector of n partial derivatives evaluated at your current point. It gives you the direction of steepest ascent or steepest descent, and you just go down by some step size eta. So you move down a little bit, right? And typically this eta here can actually depend on t. You typically want to have large step sizes initially, so you make big jumps towards your optimum. And once you're further down the line for bigger t, and you're closer to the optimum, you want to take smaller steps so that you don't overshoot. So very often this eta actually scales like 1/t or 1/√t or something like that. Right, and you just repeat until you're happy. And this method is just enormously useful. It's used all over the place. It's studied very extensively. Very often there's pretty fast convergence. This is a good method. And we want to speed it up. And in some cases, quantum computers can speed it up, not so much by reducing the number of iterations, but by just speeding up the cost of one iteration. Right? If you look at this algorithm here, the most expensive step is clearly computing the gradient, which is an n-dimensional vector. And you want to, but in every iteration, you have to compute this gradient again, either exactly or approximately. And in some cases, quantum computers can compute this gradient much better, much faster. So I want to sketch this in one slide. And this is due to Stephen Jordan in 2004. Let me sketch it for the case where, so Jordan actually assumed that f is approximately linear around the point where you want to evaluate the gradient. Right, so let's say we want to evaluate the vector of partial derivatives, the gradient, at some point z. Let's assume for notational simplicity that z is the 0 point. Right, then the assumption that f is approximately linear means you can write it like this. Right, and I'm going to use these approx symbols all over the place. This is just a sketch. It's not very rigorous. And if you have something that's close to a linear function, then what is the gradient? Well, the gradient is essentially these vectors of linear coefficients here, a1 up to an. So this is what the vector that you want to extract efficiently. And suppose we can compute our function in the phase. So suppose we have an oracle that takes cat x. Cat x would be an input to your function. So let's say a vector of n real numbers in finite precision. And suppose we can compute the value at f at that point, and we can put it in the phase. Right? If you just can compute the value of f in a bunch of bits, that's good enough because you can put that in the phase and uncompute. So this is not an unreasonable assumption that we can do this. Now, so here's a simple quantum algorithm to extract this vector a1 up to an, to extract the gradient at the point z. So we first take a finite grid of equally spaced points around each entry zj. Right? Remember, z is the point at which we want to evaluate the gradient. And we set up a uniform superposition where every coordinate of x sort of ranges uniformly over that grid. This is very easy to compute on a quantum computer. And then we compute in superposition, we compute this function value in the phase. And because the function value is essentially a linear function, some nice factorization happens. So first of all, this A0 here, this sort of comes out of the sum. It's a global phase and it doesn't matter. The other parts, it really very nicely factors into n pieces. So approximately what you have created now is a global phase, which is irrelevant, and then an n-fold tensor product, where each of the product states is essentially the Fourier transform of the number aj that you're trying to extract. So what do you do now? You just separately to each of these n registers, you do an inverse Fourier transform, and you get the numbers a1 up to an. Right, and this is of course nothing else but the Bernstein-Vazirani algorithm, but done in real space instead of in binary space. Right, Bernstein-Vazirani algorithm is exactly the same thing, but it recovers the coefficients of a linear function over f2 instead of a linear function over the reals. This is a very simple trick, and we should notice here that the time complexity is not constant here, but the number of calls you make to f is constant. So if you want to compute a gradient of a pretty expensive function, this can actually be a very good thing. And there's an issue here. The issue is in this approximation symbol here. Like every function that's sort of somewhat smooth, of course, if you look very closely around z, it's going to be very linear around z, right? Because the higher order terms of its Taylor series, they don't matter too much. But maybe you have to be extremely close to z when you're evaluating your function in order to pick up this linear behavior. That's going to be expensive. It would also require computing your function f with a very high precision. Right, so there was a subsequent paper after Jordan's paper by Gillian, Arunachalam, and Wiebe for the case where f is not so close to a linear function, but maybe it's close to a somewhat higher degree polynomial. And they did essentially the same thing with higher order interpolation formulas. So when f is not well approximated by linear, but by a low degree polynomial. And then you could do pretty similar tricks. The number of function evaluations is no longer constant, but it's still a lot better than what it would be classically. Right, so this is a pretty useful general trick to compute gradients, at least approximately compute gradients. The next thing I want to talk about is another workhorse of continuous optimization, and that's linear programs. What is a linear program? A linear program is something that maximizes or minimizes a linear function. In this case, I start with a maximizing linear program. And the variable you can play with here is an n-dimensional real vector. So you have real numbers x1 up to xn. This is what you can move around. This is what you can play with. And you want to maximize this linear function. Right, so C is a fixed vector here. It gives you sort of the costs. And C transpose X, this is just sum over I, Ci Xi. It's a weighted linear combination of the Xi's. This is the thing you want to maximize. And you have a number of linear constraints given by these vectors Aj. So for J running from 1 up to M is the number of linear constraints. You want it Aj transpose X is at most Bj. And you also want your vector X to be non-negative. This is a canonical form for linear programming. Right, so the input is the vector C that specifies your objective function. The vectors Aj and the numbers bj that specify your linear constraints. And then x is your variable that you can try to maximize over. And this has been a very important tool in continuous optimization since at least the 1940s. This is due to the simplex method, which is exponential time in the worst case, but pretty efficient in practice. And you can even do polynomial time in the worst case by, for instance, the ellipsoid method, which was invented by Kacheljian, or at least applied by Kacheljian to linear programming in the late 70s. And so this is a very important general tool. It can be used to optimize all sorts of processes in factories, etc. The way you sort of distribute the resources over different processes. Very often you can capture these things with linear programs and you can then efficiently optimize. And you can generalize linear program to something called semi-definite programs. And here what you do is you just replace the non-negative n-dimensional vector x, which is the variable in an LP. You replace it by an n by n positive semi-definite matrix, which I will denote by capital X. And everything else remains basically the same. So the trace of a fixed matrix C times X, this is really just a linear combination of all the n squared entries of the matrix X. So it's still a linear function that you're trying to optimize over your variable capital X. And similarly, you can have linear constraints specified by matrices AJ and numbers BJ. And the constraint that X in the LP needs to be a non-negative vector is replaced by the constraint that capital X in the SDP needs to be a PSD matrix. And just like for LPs, there's a beautiful duality theory for these things. So under mild assumptions, this maximization program is equivalent to this minimization program. And somehow the constraints and the variables change place here. So on the left, you had an n by n variable matrix, and you had m constraints. And on the right, you have an m-dimensional variable vector y, and you have one big PSD constraint on n by n matrices. And for my next slide, it's going to be convenient to put some trace upper bound on x so that x is not unbounded. I'm going to assume that the trace of x is at most r. I'm adding this as a constraint to my primal program. So the program on the left is called the primal. The program on the left is called the primal. The one on the right is called the dual. So I'm adding this constraint here to the primal just to make it a bounded problem. Of course, this also affects the dual. It affects it in this way. So I'm just adding a little bit of stuff to the dual here to make a nice primal dual pair again. And the good thing about these STPs is they look a lot more complicated than LPs. To some extent they are. They actually have a lot more expressive power. I already mentioned this SDP-based algorithm of Goemans and Williamson to approximate the maximal cut in a graph as well as we can in polynomial time. The good thing is it's still solvable efficiently. For instance, using the ellipsoid method that was also used for LPs. And there's a technical issue here that you might not get to the exact optimal solution. So we typically want to approximate the optimal value here up to some additive error epsilon. And one way to do that is to sort of add an additional constraint to the dual where you say, I want that BTY is at most some number alpha. If you do this and you check for feasibility of this dual, you're actually deciding whether the optimal value is at most alpha or not. If the optimal value is less than alpha, then your modified dual is still going to be feasible. And by varying alpha, these feasibility problems then allow you to do binary search to find the optimal value. Right, and again, this is all classical. I want to talk about quantum. So there's this recent development from the last few years that there are better quantum SDP solvers, and they start from something called the Aurora-Kale state-based solver. And I probably made a mistake with this slide in the sense that I tried to cram the classical SDP solver as well as its quantization into one slide. So this is going to be a very dense slide, and I apologize in advance for that. But it has the advantage that I don't have to leave back and forth while explaining how to quantize the Aurora-Kale SDP solver. Right, so if your epsilon, the additive error you allow in approximating the optimal value is kind of big, think 1/1000. So it shouldn't be exponentially small, shouldn't be polynomial small, but let's say small constant. Then the best classical SDP solver is the multiplicative weights method of Arora and Kale. And you should think of this as an iterative method to sort of do binary search on the optimal value by deciding feasibility. That's what I sketched at the end of the last slide. So we're sort of adding a constraint to the dual problem, saying that the optimal value is less than alpha, and then we're checking if that's feasible or not. If it's feasible, the optimal value is less than alpha, and we can continue our binary search. If it's not feasible, the optimal value is bigger than alpha, and we can continue our binary search. And the idea of this Arora-Kale solver is you sort of bouncing back and forth between imperfect solutions of the primal and the dual. And it turns out that this converges amazingly quickly. So we're going to start here. Let me briefly remind you of what the primal and the dual look like. So I had this trace constraint on X, and for exposition, I'm just going to put this R equal to 1. Right, so let's start simple. Let's start with sort of an attempt at a feasible solution for the primal. Let's just take the matrix identity over N. At least it's PSD and its trace is 1. So those two constraints are satisfied. And now the thing is that you can derive from this sort of purported attempt at a feasible solution for the primal, you can derive a very relaxed version of the dual problem. And this relaxed version is just going to be a linear program with only 2 constraints. And it looks like this. And this looks kind of complicated. So let me just sort of point out the different pieces here. This is the same objective function we already had before. This is this new constraint that we're adding, which is sort of claiming that the optimal value is at most alpha. And this here, this is just one linear constraint. So I've kind of replaced the matrices AJ by the trace inner product between X0 and AJ. So what we have here, this is just one linear constraint, and here's another linear constraint. So this is a very simple LP now. There's only 2 linear constraints, ignoring the non-negativity conditions. And let me very quickly browse back to the dual to show you where this comes from and why this is a relaxation of the dual. Right, if you look at this big PSD constraint that's happening in the dual here, this statement here is equivalent to saying that for every PSD matrix X, if I take trace inner product of the left-hand side with that X and trace inner product of the right-hand side with that same X, I get an inequality between numbers. And if that inequality is true for every possible PSD matrix X, that's equivalent to this constraint here. And now I'm going to relax this by saying I only want that inequality to hold for the particular X0 that I started with for my reported primal solution. So I'm sort of taking the inner product here between AJ and I and C with this matrix X0. And that's exactly what gives me this linear constraint here, right? And this is no longer a linear constraint between matrices. This is one linear inequality involving the real numbers Yj. And it's possible that this very simple LP is infeasible. If it's infeasible, I know that the optimum must be bigger than alpha, and I can stop and I can continue my binary search with another value for alpha. If, on the other hand, this relaxed dual has a solution, a vector y that is a solution, I can use that to define this matrix H. I'm not going to explain the intuition of why we're defining this H, but this H can then be used to define a new attempt at a primal feasible solution, X1. And this is going to be e to the minus eta times H0. And this proportional symbol here means I'm going to divide by the trace so that it's the trace of X1 is 1, as it should be. This again induces another relaxed dual, again with only 2 linear constraints, which is either infeasible and then I'm done, or I can solve it. If I can solve it, this gives me an update for the matrix H. So I get a new matrix H1. This I can use to define my next point, X2, etc. And this sort of bounces back and forth between all sorts of imperfect primal solutions, imperfect dual solutions. And then a miracle occurs, the miracle of the multiplicative weights method. If none of these relaxed duals is actually infeasible, then this will converge in roughly log many iterations. This is going to converge to an epsilon optimal primal feasible solution. And this is kind of amazing. And I'm seeing it's already 9, so I will probably have to speed up a little bit. And this is all classical, right? This is an explanation of this Arora-Kale classical SDP solver. And then in 2016, Brandao and Svore, they had the great idea to interpret this thing in quantum terms, right? Because what are these x's here? these X's, they are n by n PSD matrices of trace 1, right? We know these things as density matrices, mixed states. So you can actually interpret these XTs as log n qubit quantum states. And they're not just arbitrary log n qubit quantum states. Like any physicist will tell you that what is this thing here? This thing is a thermal state with respect to Hamiltonian H1 and inverse temperature eta. And we have quantum algorithms to prepare such states, also known as Gibbs states. So you can prepare these primal solutions as quantum states, as log n qubit mixed states. You can then use those quantum states to sort of approximate these numbers here that give you your relaxed dual, and so on. And if you put these things together, you actually get a faster quantum algorithm.
Ronald,
yeah.
There is a question in the chat for the classical part by Devdutt. Are the primal solutions feasible at each step?
They're not, no. You sort of converge to something that's almost feasible after about logarithmically many iterations. In fact, what you really do is you run this thing for order log n times, and you take the average of the different x's, you tweak it a little bit, and then you get a primal feasible solution.
Great, thanks.
Yeah, so this was the great idea of Brandao and Svore. This was then improved by a bunch of people, including myself and my students, and also Brandao, Svore, and the Maryland group. And currently the best result is by Van Apeldoorn and Gillian. And they showed that if you start with S-sparse SDPs, and this means that the constrained matrices and the objective matrix C, that each row and each column have at most S non-zero entries, you can solve these SDPs. You can get an epsilon optimal optimizer in this time here. And don't stare at this for too long. The main thing to observe here is that this is like a very nice polynomial speedup in terms of M and N. And actually the dependence on epsilon is a little bit worse than classically. So this is a good algorithm for relatively large epsilon. So this is what I wanted to say about SDPs. I probably need about between 5 and 10 minutes, Umesh. Should I rush or what shall I do?
If you could keep it to five minutes, that should be fine.
Okay, good. Let me try. Okay, so LPs and SDPs are special cases of general convex optimization, and I want to sketch here two very general results that are known about quantum speedups for general convex opt problems. So the idea here is you're given a convex function f over a convex set k of feasible solutions, and you want to minimize it. And let's say up to additive error epsilon. It's typically too hard to optimize these things perfectly. And I have a positive and a negative result about this. And given that these are trying times, I want to start with a positive result. And the positive result is that, so classically, you can ask yourself, what kind of access will I have to this convex set? And there's many different ways to access it. You could, for instance, maybe you can ask membership queries, or maybe you can ask separation queries. A separation query is something like a membership query in K, but if your point is outside of K, then your oracle also tells you a separating hyperplane, so it gives you extra information. You can also think of optimization access to K. That's really the problem you want to solve. So there the input would be a linear function and the output would be a minimizer of that linear function over K. And all these things have long been known to be polynomial time equivalent. This was done by Grötschel, Lovas, and Schrijver in the 80s. And the good thing is that some of these reductions between these different types of access, you can really speed them up in the quantum case. For instance, you can implement a separation oracle using only a logarithmic number, O tilde 1, runs for a membership query. And that's an exponential speedup over, this is in fact one of the few exponential speedups in this whole talk. And it's unfortunately only an exponential speedup in query complexity, not in time complexity. And if you can do separation queries very efficiently, you can also do optimization very efficiently, because it's known that with order n separation queries, you can do optimization. So this induces then a quadratic speedup over the best classical optimization algorithm. And then the negative result is, so it's known that classical gradient descent for a function that's G Lipschitz, so that's kind of smooth, from a point that's at distance r from the unknown optimizer, needs this many queries to a gradient oracle, to a first order oracle. And this is known to be optimal. And there's a very recent result by Garg, Kothari, Netrapalli, and Sharif that even in the quantum case, this is optimal. So there's no sort of generic black box speedup, quantum speedup for gradient descent. This is my penultimate slide before the summary. So I also wanted to say a little bit more about non-convex optimization. Again, a very recent interesting result. It was in QIP this year. So if G is not convex, if you're outside of the convex opt region, you have the problem of saddle points. So gradient descent sort of tries to go towards a local minimum, and it kind of stops when the gradient has become 0. If your function is convex, this is a local minimum and even a global minimum. If your function is not convex, things like this picture could happen. I don't know if you see the red dot here, but it is at a saddle point of the function. The gradient is going to be 0 at that point, but it's clearly not even at the local minimum. And there's classical ways to sort of escape from saddle points. And the way that works is you basically do gradient descent for a few steps, and then you start shaking your point a little bit to escape from the saddle point. It's somewhat similar to what happens in simulated annealing, but you can analyze it rigorously. And Zhang, Lang, and Li, just this year, they showed that you can speed this up somewhat by replacing the classical shaking by a very nice quantum shaking that's based on Hamiltonian simulation. And last but not least, I want to say a little bit about the HHL algorithm, because you might think, why on earth have I not mentioned the HHL algorithm yet? It should be super useful for optimization. Right, so what does HHL do? I give you a matrix A, I give you a vector B. HHL gives you the solution vector X of the linear system as a quantum state. So the vector of amplitudes of the state ket X, this is going to be the solution to your linear system. And this should be very useful. And I know of 2 examples in optimization where this has been applied. One is a polynomial speedup for finite element methods due to Montanaro and Pallister. Finite element methods are a way to sort of solve a discretized version of a system of differential equations. So they use HHL, right? The headline of HHL is that it sometimes gives you an exponential speedup, but if you do it properly in this case, Montanaro and Pallister actually end up with a polynomial speedup. And the other example I wanted to mention is a quantum interior point method due to Kerenidis and Prakash. Interior point methods are one of the most important sort of general solvers for convex optimization problems. They're iterative, and in each iteration, they solve a linear system, so-called Newton system. So Kerenidis and Prakash, what do? They use HHL to solve this linear system. But then something very nasty happens. They sort of, so you get sort of the delta of your point, you get it as a quantum state, but you actually want to be able to classically update your point. So they solve this Newton system using all the power of quantum computing, and then they have to measure the state multiple times in order to actually classically learn how to modify their state. How to modify their current point in the interior point algorithm. So this is sort of interesting, but it's also somewhat unsatisfactory, and it's also one of my open questions. So let me go to the summary. I emphasize this. I think faster optimization is one of the main potential applications. Emphasis on the word potential here because of these issues that I mentioned before. Right, quadratic speedups are not great. You need large instance size. QRAM is an issue. We have many speedups, usually polynomial. I went over some of them in this talk. And let me end with a few open problems. So one is, I think we should try to find better quantum interior point methods. I think this Kerenidis-Prakash algorithm is a good start, but it's not. It's probably not the best answer we can give. If you look at quantum speedups for iterative methods, they typically improve the cost per iteration. That's true for these STP solvers that I mentioned. It's also true for other things that I didn't mention, like quantum speedups for boosting and matrix scaling. And it would be very nice to find examples where we can also speed up the number of iterations, like reduce the number of iterations. I'm not aware of any of those. Can we solve the traveling salesman problem with a quadratic speedup? Lots of journalists say that we can solve TSP in polynomial time. We don't even have a quadratic speedup yet. And last one is something like approximate max flow in weighted graphs. So there's a very nice classical development in algorithms that uses electrical networks and Laplacian solvers to efficiently approximate max flow. And the question is whether we can speed this up, get it down to sublinear time. So with apologies for going over time, this ends my talk.
Thanks, Ronald. That was a fantastic survey of quantum optimization methods. So let me see if there are any questions, Anurag or Chinmay.
Yeah, so one question from the chat is, do you have any opinions on the variation algorithms such as QAOA?
Yeah, I mean, I sort of consciously sort of bracketed them at the start of my talk. I don't know too much about them. I know that an enormous amount of people are working on this stuff. Like most of the quantum algorithms that you see appear on QuantViz, they tend to be variational algorithms. I think part of the reason is it's easy to write a paper about variational algorithms. Right, you just have some heuristic, you implement it on a 5-qubit IBM computer. It doesn't really mean very much, but so I think it's interesting because we can experiment with them, but I have not seen strong indications that these things really speed up over even very simple classical algorithms. So Matt Hastings has a nice paper where he has a sort of a class of classical local search algorithms that perform at least as well as things like QAOA. So I think the jury is out on the usefulness of variational algorithms in optimization, that is. I'm all for variational algorithms in chemistry. I think something like VQE is a very good idea. Not sure if I fully answered that question, but
Right, hope so. Thanks. Yeah, so Marika says that was very helpful. And another question is, would there be, the question is by Devdutt, would there be quantum speedups for projected gradient methods for constraint optimization problems?
Yeah, that's a good point. Yeah, so the way I sketched gradient descent is as a sort of unconstrained problem where you just move in the direction of gradient. You don't have to worry about feasibility. But of course, it's possible that your gradient step takes you outside of your set K of feasible solutions, and then you have to project it back. Probably some of the things that I mentioned, like these STP solvers, you can probably think of them as projected gradient descent, but I don't know enough about it to be certain here. It's actually a pretty nice idea, right? Because you could use quantum measurements to try to do the projection. I'm not sure if there's any like deep work on this.
Great, thanks. So Umesh, do we have time for 2 more questions? I think there's one on the chat.
Yeah, let's do at least one more question.
Oh, one more. Yeah. So there's one question from Q&A by Alessandro Luongo. Do you think the quantum approach for zero-sum games is any relevant for LP optimization, or is the error dependence too big?
I mentioned these STP solvers, which have a certain complexity. And there are actually slightly better quantum LP solvers. So if you look at the special case of STPs where the matrices are diagonal, you get back to linear programs. And the best quantum algorithm for solving LPs is based on these zero-sum games. And its asymptotic complexity is slightly better than what I mentioned for general STPs.
Great, thanks.
Great. Okay, well, great. Thanks, Ronald. So let's move on to the panel. So if you
Stop sharing.